Imagine a bug hiding inside the Linux kernel for 15 years, surviving a countless update and security audits. Then an automated tool finds it. That bug is GhostLock CVE 2026-499. It's a high-severity vulnerability that lets an unprivileged user gain root access in about 5 seconds. So in this video, we break down how it works, why it stays hidden for so long, and how the exploit turn a tiny kernel bug into the full system compromise. Let's dive in. So let's kick things off with our first slide. So, GhostLock is incredibly long-lived vulnerability. It was introduced all the way back in May 2011 with the release of Linux kernel 2.6.39 for 15 years. So this bug silently existed in virtually every major Linux distribution. Think about that. For example, throughout the entire rise of the modern cloud infrastructure like Docker, Kubernetes, and enterprise Linux, this local root vector was sleeping in the codebase. So let's look at the spec sheet for this vulnerability to understand the threat profile. Uh, the, the threat profile is like that. It tracked as CV 2026 43499 with a CVS score of 7.8. It's represent a local privilege escalation and a complete container escape. The prerequisite is it required the kernel to build with config futex pi equal to y. This is crucial. And priority inheritance futex support is enabled by default on virtually every enterprise and desktop distribution. There is no special user privilege or namespace required to trigger it. So the flaw is it's at its core, the GhostLock is the logical error in statement management during the deadlock rollback scenario, and this logic error directly leads to a stack use after free or UAF in kernel locking rt mutex.c. And it was discovered by a Nebula security automated kernel analysis tool it named Vega. So it's a testament to how automated formal analysis can uncover deeply nested logic bug that manual code reviewer missed for a decade. So to understand why this bug happened, we have to establish some first principle. What is the futex? A futex is a stand for fast user space mutex in a normal or non-contended condition. Lock accusation happen entirely in user space without costly system call. The kernel is only invoked when there is a contention, meaning thread A holding the lock and thread B must go to sleep waiting for it. And now, what is the priority inversion? Look at the left side of the slide diagram. Suppose we have a low priority task holding a lock. A high priority task arrive and want to go that same lock. So the high priority task um, has to wait, and this is the priority bottleneck. To solve this, the kernel implement priority inheritance or PI shown on the right side of the slide here. Um, so when a high priority task block on a clock held by low priority task, the kernel temporarily boosts the priority of the low priority lock holder to match the waiting task, and this ensures the low priority task finish its work quickly and release the lock and yields to the high priority task. So under the hood, this entire boosting and unboosting process is managed by RT mutex or real-time mutex structure in the kernel. So if a priority inheritance wasn't complex enough, the kernel introduced an optimization called Futex, compare require PI. Imagine you have a multiple thread sleeping on on a traditional non-PI Futex. I mean, like A, and you want to wake one up and transfer the rest to wait on a PI aware real-time mutex like B, and instead of waking every single thread up just to have them immediately block on lock B, which would cause a massive context switching storm, the kernel perform a surgical transfer. So it directly moved the waiter structure from the lock A's wait queue to lock B priority queue while the thread remains asleep. Because this waiter structure exists as a RT mutex waiter object on the sleeping thread, the kernel stack, the kernel is actively manipulate the memory across the different task stack, and these create intense state tracking, complex and fragile ownership rule. So this brings us to the structural flaw in kernel locking RT mutex. Let's look at the function remove waiter. So this function is responsible for tearing down the blocking request when the task decides to stop waiting. And the fatal assumption here is that the thread executing the cleanup is always a thread that owns the waiter object. So as you can see in the legacy code, we have the current PI block on equal lock. So the code assumes that the current the active and running task is one whose blocking state need to be clear. But as we just learned during the requeuePI operation, the kernel can modify and track the waiter on behalf of other sleeping thread. And this assumption is the crack in the foundation. So how does an attacker break this assumption? By forcing a deadlock rollback, the attacker set up a three coordinated thread A, B, C, and tributes to intentionally construct a circular priority inversion deadlock. And then the kernel attempts to perform the requeuePI operation. Its internal lock validation detects this cycle to prevent the system from freezing. The kernel aborts the operation and return the error code edlk. So here is where the disaster occurs actually. And during the rollback, the kernel must unwind the state of the sleeping thread. I mean, it's called the remote waiter function to clean up, because the remote waiter function assumes the execution thread is the owner, and it mistakenly modified the state of the wrong task, and specifically PI block on is cleared on task A while the actual waiter structure belongs to the task B. So let's visual the system how it collapsed in this slide. Because of the rollback error, task B is woken up with error, and task B finish the execution, exit its active kernel function, and its stack frame is completely turned down and freed. However, because the kernel cleared the bookkeeping on the wrong task, I mean the task A, the active kernel list still think um, test B vector structure is active and registered. So the kernel is now left holding dangling pointer pointing directly into the freed inactive region of the test B kernel stack. So now we enter the exploitation phase. How does an attacker weaponize a dangling stack pointer? First, they must reclaim the freed stack space because the kernel stack layout are highly predictable. The attacker can execute standard system calls such as the set XATTR or MSG and SND to perform a memory spray, and by spraying control data over the recently freed stack area, an attacker can perfectly align the forge RT mutex beta structure right where the dangling pointer is looking, and the kernel now uh, unknowingly hold the pointer to an attacker controlled fake structure. So, and the fake structure is a place the stack used after free is upgraded to an exploitation primitive. So the fake RT mutex vector contain internal pointer for circular doubly linked list, and when another process interact with the lock or when the lock state is cleanup, the kernel attempt to update the list using the standard list manipulation function like list delete or list add, and by setting the fake list pointer to point the target kernel address, the attacker exploit the list manipulation logic when the kernel execute, for example, list delete function, and it write the pointer value to arbitrary address chosen by the attacker, and this unlock our first major primitive, I mean the constraint arbitrary-write. So while a constraint write, the attacker execute the final exploit chain, and I mean that, for example, it break the KSLR. So the attacker leak kernel pointer by spraying and reading back the stack value to bypass the kernel address space layout randomization or KSLR, and it overrides the target path by using the right primitive. They target the kernel structure like mode prop path or core pattern, and they hijack the control flow by redirecting these path to the user space helper. They hijack the kernel space execution, and they escalate the privilege by control flow replace the by hijacking the control flow and replacing the exploit process credential with the UID 0, I mean root, and it strips away namespace and break out of any container CG group. So the entire process completes is under 5 seconds, so it's very interestingly, and you can achieve stable and interactive root shell. So let's talk about the real world impact of this flaw, especially in multi-tenant or shared hosting environment. So on an unpatched host, and the security boundary is the paper thin, and attackers start by exploiting a standard web application vulnerability like an outdated WordPress plugin or PHP FPM vulnerability. So normally the attacker is confined to that site, isolated container or KJP sandbox. So, but with the GhostLock, that low privilege PHP process can call the Futex system call and trigger the stack UAF and immediately escalate to the host root. And they bypass every container boundary, giving them complete access to every other customer file, database, and backup on the physical server. So this is the ultimate nightmare scenario for hosting provider. So, um, So how was this fixed? Let's analyze the patch and commit 3BFDC blah blah blah. So as you can see in the green highlighted diff, um, the fix adds a validation check to ensure that a vector being cleaned up is actually owned by the current execution task. I mean, if vector is bigger or equal than task current. So if it's not, the kernel does not clear the PI block on the execution task and preventing the state corruption and safely handling the deadlock rollback without leaving a dangling pointer. Note that the following commit in the CV 2026-53166 was actually reverted upstream because it caused the regression, meaning this single check is a primary line of the defense. So how do we secure our system against the GhostLock? We have three options. The first option is a runtime mitigation or SecCom. You can block the priority inheritance Futex system call like Futex like PI, Futex wait require PI, Futex comp requeue PI, and using uh, second profile, but this is highly disruptive because it's break the legitimate application that rely on the glibc priority inheritance mutex. So the second operation and option you can do is the kernel update. You can update your distribution kernel and reboot. So Alma Linux and Cloud Linux have already shipped production patch with the kernel care live patch for zero downtime environment, and the live patch can be injected directly into the running memory and fixing the logic in remove waiter without requiring a reboot. So to verify if your server are safe, you have two clear methods. If you perform a standard kernel update, run uname dot dash r and verify your kernel version. It's at or above the patch release, such as the version 5.14, blah blah blah. And if you are utilizing the live patch, use the command keyctl --patch info grep cv 2026 43499, and do not use the general --info flag here, as it may return an empty output despite being correctly patched. So always look specifically for the CV identifier. And to wrap things up, let's look at the engineering synthesis of this bug. Why did it take 15 years to find? Because the GhostLock sits at the exact interaction of three highly complex domains. I mean, the Futex PI state machine, the like rollback recovery, and the stack lifecycle. So a failure in one of these are rare, and they uh, when they when they aligned, and so it's maybe occur a logic bug, and this bug was born at that intersection. And the key takeaways are very clear. So it means that the legacy does not mean secure. So just because the code is old and stable does not mean it's safe. And state management is harder than the memory management. I mean, the logical flaw is a state machine inevitably lead to memory corruption, and we need the defense in depth. We must assume our kernel boundary can be breached or maintain rapid, and we should patch the pipeline to protect the workflow. And this is the story of the GhostLock, a 15-year-old bug that shows us just how complex modern operation system really are. And if you want to read more about the technical write-up or check out the patch, I have left a link into the resource in the description below. And if you enjoyed this technical breakdown, make sure you smash the like button, subscribe to InfoSecTube, and hit the notification bell so you never miss another deep dive. And let me know if you have any comment or if you have. And I have a question for you. So, what is the oldest bug you have ever found in your production? So, let me know in the comment. And until the next time, keep your system patched and secure and do the secure coding. So, I will see you until the next video. See you guys.